Not very realistic because for every system you should have some energy loss. But in theory, we can discuss in this manner. This is something you can observe from this picture. Right? Firstly, the first pawn tells you the initial conditions, and then the vibration amity remain unchanged if you play with undamped conditions. The amplitude, I use U0 here to denote amplitude. And then you can measure the vibration period. Period means the time required to complete one vibration cycle. We call that period. Period is also one important property to describe the dynamic system. Initial pawn, period, and vibration amplitude. There are some relationship between period and frequency. At the beginning, you have learned what is natural frequency. Natural frequency omega n equal to square root k of n. Remember this equation, omega n. Why I keep emphasizing this term, because at this moment, I believe that all of you can remember this equation. But near the end of this module, you need to learn many different equations, many different theories. At the end of this semester, I believe that some of you will forget these equations. So in the problem, in some simple questions, I give you directly the K and M, but some students cannot find out the frequency during the examinations. That's why please remember this important formula. If you know stimulus, if you know mass, then actually you can calculate natural frequency. Okay, not unknown. I'll go back to this line. There are some relationship between frequency, period, this kind of property. Period, vibration period, Tn, as shown on the previous slide, previous picture, is equal to 2 pi over omega n. So if you know frequency, you can calculate vibration period. Vibration period is one very useful indicator, especially for buildings. I will mention a little bit later. Building, a tall building has a vibration period, normally a few seconds. The taller the building, the larger the vibration period. Then you can change the formula a little bit. You know omega n, right? You know omega n. So period is equal to 2 pi square root mass over stimulus. Just combine omega n and Tn together, right? You know omega n, so you can change the formula a little bit. The larger the mass, the larger the vibration period. It takes more time. Larger period means it takes longer time to complete one vibration cycle. If it is a building, if it is a structure, which means it takes more time to complete one vibration cycle back to the original position. Another frequency that we normally use for mechanical problems, we call that cyclic frequency. Cyclic frequency means the frequency measured in hertz. The number of cycles per second, hertz, number of cycles per second. It's also related to period or natural frequency. Natural frequency, omega n, the unit is measured using radian per second. Radian is the angle, right? Angle, the measurement of angle using radian per second. So here we have three terms: omega n, natural frequency, natural period, and then you have cyclic frequency. In this module, we normally use omega n or natural period. Omega n natural period. Sometime for more information, I may give you that cyclic frequency sometime, but not always. So what is the term natural? Natural frequency, natural period, what is the meaning of natural? Natural simply means this property depends on the system property itself. Natural vibration property, period, frequency, we call it natural because this kind of parameter depends only on the structural property, stiffness, and mass. Nothing to do with the loading. Nothing to do with the other properties. So here we give them a term called natural. Just depends on the system itself, K and M. Okay, some further discussions. Well, from the previous sections, we know the solution for an undamped system under free vibrations. You can express them mathematically, cosine, sine function. You know the coefficient A, you know the coefficient B. They depends on the initial conditions and also omega n. You know how to calculate omega n based on stiffness, based on mass. Mathematically, you can combine cosine, sine into one trigonometric function. You can combine sine, cosine into either sine or cosine function based on our mathematics. So actually, you can express the system vibration using another form, using only one cosine function. But you have to change the angle a little bit. When you add up sine cosine function together into one single function, there is a phase angle inside the cosine function. We call that theta. And then the vibration amplitude is called rho. Rho is a Greek symbol. You can use this alternative form to represent the displacement functions. Well, in terms of calculation, I think the original form is more easy to use in terms of calculation. But in terms of the graphical understanding, I think the alternative form is more easy to understand graphically. Because from the graph, from these equations, you can see the vibration amplitude, right? Cosine function, what is the maximum value of cosine function? 1. The minimum value, -1. Right. Cosine function, the magnitude is 1. So the vibration amplitude of this displacement function is basically governed by rho, the coefficients. That's why I think this alternative form is more easy to understand, because you can see the vibration amplitude immediately. And then you can also understand the vibration pattern, cosine, with a phase shape, with a phase angle. What is so-called cosine? What is the shape of cosine function? Cosine function. Cosine t, for example, omega t. If you plot a cosine function graphically, it becomes something like this. At the beginning, maximum 1, and then -1, and then 1, right? Cosine functions for cosine omega t. But in case if there is a phase shape, if there is a phase angle inside the cosine function, what is the consequence if there is one angle right here? It will make the graph shift left or shift right. So the starting point is not the maximum point. Okay, if there is an angle inside the cosine functions, just like the picture at the bottom. The maximum value is not occurred at the beginning. There is some shifting horizontally. It may be earlier or it may be later. Okay? This is how you understand these equations. I think it's good to understand graphically and mathematically. Anyway, they describe the same problem. Okay, if you answer the problem, if I ask you, hey, what is the displacement function for a free vibration system without damping, then you can simply put down any one of them. You may use the original one, or you may use the alternative form. They are both correct. Depends on which one you are more preferred to. But another remark is that these two equations only for system with no damping. Okay. Only for a system without damping. If there is damping, then you have to use another equation in the next sections. Okay, don't use the wrong formula. Don't use the wrong formula. I allow you to use the given formula in the exam in quiz, but please put down the correct version. These two are just for a system without damping, because we derived them for an undamped system at the beginning. The next section, I will show you what happened for a damped system, which is more general. You can find out the vibration amplitude. Some textbooks use a rho to denote the vibration amplitude. Some put a subscript, 0 here, to denote the vibration amplitude. Depends on the notation you use. Anyway, the amplitude is equal to the initial displacement squared plus initial velocity over omega squared, and the take the square root. It's quite easy to remember this equation if you understand this equation. This is A, right? This is B. The amplitude is simply equal to A squared plus B squared. So if you know A, if you know B, then you can use this simple equation to find the vibration amplitude. Phase angle is equal to B over A, and then take the tangent, arctangent here. Help you to find a phase angle theta. This alternative form is more easy to understand. You can see the vibration amplitude, you can see the shape of vibration easily. But you need to take some extra calculation in order to evaluate the amplitude and phase angle. If you use this alternative form, you have to find out rho and theta yourself. That's why in terms of calculation, I think using the first one is more easy in terms of your calculation. But in terms of physical meaning, the second one is more rich in physical meaning. But you have to take some extra calculation to find out rho, to find out phase angle. Don't make mistake if you want to do so. Okay, there are two equivalent equations. Okay, one very simple example. Suppose we have a single degree of freedom system, a firm structures. Actually, you have seen this one before in topic 4. In topic 4, example 1, the structure is in this way. You may go back to topic 4. But this time we ignore damping. So I remove the damper. I remove the damper from the system. In this example, we have a single degree of freedom system with rigid beam assumptions. Assume that the beam is perfectly rigid. The stiffness provided by column. Two massless column. What we're going to do? We are going to determine the natural frequency and natural period for the following system without damping. Natural frequency. Natural frequency means omega n. Natural periods mean Tn, symbolically. In this example, you are asked to determine natural frequency, omega n, and natural period, Tn, for the following single degree of freedom systems. If you remember the formula, this becomes a very simple example, because omega n is equal to what? Is equal to K over n. Period. By definition, period equal to 2 pi over omega n. So if you know natural frequency, you can immediately obtain natural period. They are equivalent parameters. One measures the time required to complete one vibration cycle. The other one calculates the number, the revolution in terms of radian per second. So you can see that if you want to determine omega n or the natural frequency or natural period, you need to know what is the stiffness of the system. You need to know what is the mass of the whole system. If you put down the equation of motion and you double dot, we have no damping, right? We have no damping, so I ignore the damping terms. Equal to 0, free vibrations. Which means if you know mass, if you know stiffness, then you can immediately obtain omega n and natural period Tn. Mass is mass, nothing to do. Mass just a single number. Stiffness, you have to calculate stiffness yourself based on the column property in this problem. Column stiffness, column fracture rigidity, EIC. The height we normally call this H. The beam is rigid beam assumptions. I believe that we can calculate stiffness immediately. Stiffness, if we use rigid beam assumption, the column stiffness is equal to 12 EI over HK. This is what we found in in topic 4. We have 2 columns. We have 2 columns means the system stiffness is equal to 2 times the column stiffness. Parallel system, right? So you can calculate column stiffness immediately. And then over mass, then you have the natural frequency, and then you have the natural period. Example 1, just asking you to understand this equation, omega n equal to square root k over n. This one. Useful equation. Please remember these equations. Stiffness equal to 2 times the column stiffness. Column stiffness equal to 12 EI over h squared. 24 EI over h squared. So this is the natural frequency. Natural period, 2 pi over omega n. If you like, you may convert the equation to 2 pi square root mass over stiffness. You can calculate period directly because we know the formula for omega n. You can fill some number. You can fill some number to the equations. Say for example, if you notice that EI is equal to 20 mn meters squared. If you notice that the mass is equal to 190 tons, if the height is 4 meters, you can put them all together to find out the stiffness for the whole system, and then you can evaluate the numerical number for frequency and also for the period. Okay, depends on the property. If you know EI, if you know M, if you know H, you can find out the numerical numbers. Here I just express them symbolically, but actually they have some numbers. EI depends on the shape of the column. EIC depends on the shape of the column, depends on the material property, whether you are using steel or concrete. Mass depends on the density of the materials, depends on the size of the member. H, the height of the story, the height of the building. One thing is that frequency, omega n, the unit is radian per second. When you do the calculation, you can express every unit to standard unit. Standard unit mean Newton. Use Newton for force, use meter for length, use kg for mass. When you use this equation, remember to change the unit to standard unit. Okay? When you use this equation, remember to change everything to the standard unit or equivalent unit. Otherwise, the value will be totally different. Please remember to change the number km to standard unit. Newton, meter, kg, these kind of things. Otherwise, it becomes another numbers. Period equal to 2 pi over omega n. So 1 second in these structures, in this problem. It takes 1 second to complete one vibration cycle, in the other words. A more general scenario, a damped system. A damped system actually is a more general scenario. We normally do this one. Because every system, every structures, every building should have damping, should have energy loss due to friction, due to cracking, due to yielding, due to different mechanisms. So damped system is a more general scenario that we need to consider. I changed the equation of motion a little bit. This time, we consider a damped single degree of freedom system with damping. With damping means C is not zero. C is not zero. C is equal to some particular number. C is equal to some numbers. M is N. K depends on the shape of the structures. In topic 4, we play with different form of structures. For structures under horizontal vibration, for structures under vertical vibrations, we use parallel system, series system to find out this. Two initial conditions: initial displacement, initial velocity. Right here, you are asked to solve this equation, solve for this equation, find out what is U equal to something, just like the previous scenario. But this time we have damping. Well, normally, to solve this problem, we convert this problem to another form before solving it. How? We dividing the whole equation by mass. Divide the whole equation by mass. So the first term becomes u double dot. The second term becomes u of m times velocity plus k of m times u displacement equal to 0. Free vibration, right? Free vibrations mean the force equal to 0. We are still focusing on free vibrations. And then we do some modifications on the equations. Firstly, omega n equal to square root k over m, which means k over m equal to omega squared. So you can see the third terms. The third terms becomes omega n squared. We group k, m together into natural frequency. The middle terms C over m. This time we introduce one more parameter to describe damping. This parameter, this one, we call it damping ratio. Damping ratio. Did I put on the name? Here. Damping ratio. This is a Greek symbol. I remember that the pronunciation is C, XI, C. We use this symbol C to denote damping ratio. Maybe you can just call it damping ratio, okay? The Greek pronunciation, I think, is C, XI. So it's quite confusing, right? It's just like a character C. That's why I normally call this damping ratio. Otherwise, I think you will confuse. Normally, I just call this damping ratio. But when you read the dilemma textbook, normally they use this symbol to denote damping ratio. Or when you read the code of practice, the Wien code or the other code of practice, they also use this symbol to denote the damping ratio. A quite general symbol. What is damping ratio? Damping ratio is a ratio between two values. Which two? The numerator is the damping coefficients of a system. The numerator is the damping ratio of a given system. The denominator is another number called critical value, critical damping coefficients. You will know what is so-called critical on the next few pages. But mathematically, it is equal to 2m over n. I will let you know very soon what is critical values. But simply means a ratio between two numbers, C over C critical. So what is C over m? C over m, when you take a look on the definition of damping ratio, C over m is equal to 2 times omega n times damping ratio. So you can replace C over m using 2 omega n times damping ratio to replace C and m. That's why the equation here involves only two parameters after dividing by mass. Depends on damping ratio, depends on natural frequency. So you can convert the equation of motion to another form with only two parameters shown in the equation. One is damping ratio related to damping. The other one is natural frequency. Natural frequency is a very important parameter. It's talk about the ratio between stiffness and mass. It's associated to mass and stiffness using one number, one parameter. This is another form of our equation of motion. You can solve to find out what happened for our displacement, u. This slide we try to explain what is so-called critical damping coefficients. How critical is critical? We talk about the level of damping. What is damping? Damping means energy loss. Normally, every system should have damping, unless you are in a very ideal condition in vacuum, then you have no any particles surrounding you. Otherwise, normally you have damping for all systems. It may be due to yielding, cracking of concrete, friction between different elements, etc. Then what is a level of damping? For a system, you may have large damping, small damping, or normal values. The thing is, what is large? What is small? What is normal? If I tell you that, oh, we have a system with damping coefficient equal to 100, is it large value? Or if you have a system with 1,000 or 10,000 damping coefficient, is it a large number? It's quite difficult for you to make decisions, right? If I give you one number, and yeah, no way to make decisions. This one is more valuable if you measure the ratio. You can compare with some reference. So there are three scenarios. Firstly, if your damping coefficient C greater than a critical number, CCR, C critical. Alternatively, damping ratio greater than 1. In this scenario, we call that overdamp. Then what happens for a system with overdamping? When you plot them graphically, the middle picture shows you the displacement. The displacement is normalized by the vibration amplitude. So you can see that the maximum value is equal to 1 because we normalize the displacement using the amplitude. More easy to read. The x-axis is the time scale normalized by the vibration period. So you can see 1, 2, 3 here, which means 1 period, 2 period, 3 period. Make you more easy to compare with different systems. Then what happened for overdamp? Maybe I change the color to blue. For an overdamp system, you can see that the displacement decreases gradually and then reach the at-rest positions. And what we can observe from this graph, if we use the structures, to denote the vibration mode here, then what we have, actually there is no vibration. The system initially have a displacement, and then the displacement decrease gradually, and then at rest immediately at this at rest positions. This is what it's meaning. Right? There's no any oscillation. If the system is under overdamping, there is no oscillation. You can see that the displacement only lie on one side, no negative values. That means there's no oscillations. One classical example is just like here. If you have a bowl, if you have a tank of water, if there's a ball fall inside the water, the ball will normally flow upward and then stop on the level, and at rest, no any vibrations. Normally, overdamp is appeared not for structures. Normally, it's appeared for the other mechanical system. But graphically, you can understand in this manner. There is no any oscillation, but the displacement reduced gradually, and then converges to this zero displacement number. This is the first scenario, overdamp, for a system with relatively large damping. How large is large? Larger than the critical number. C, damping coefficients greater than the critical number, or damping ratio greater than 1. Then you call this large damping, overdamp. Then what is the other scenario? One is over, then the other one should be the opposite, right? Underdamp the system. For underdamp the system, mathematically, that means your damping coefficient less than the critical number, or damping ratio lesser than 1. Damping ratio lesser than 1. Then in terms of the vibration mode, you will see vibration. The structures start to oscillate back and forth about their equilibrium positions. You start to see oscillations. the structure oscillate and then converge to 0. For underdamped system, you will start to see oscillation, but the vibration amplitude decrease as time goes on. Then what is critical? Critical means this very ideal line in which damping ratio equal to 1. The boundary C equal to CR. The system is lying somewhere between oscillation and without oscillations, a very ideal scenario. We call it critically damped scenario. C equal to CR, or damping ratio equal to 1. It's just like a boundary to divide a system with oscillation and without oscillation. That's why we call that critical. Just like a boundary tells you whether you have vibration or no vibrations. Then what about the values? You can prove the values mathematically, but the previous slide I showed you the expressions already. Critical damping coefficients is equal to 2m omega n. You can prove this mathematically. I think I have some derivations later. So this line basically shows a system with different level of damping. Large damping, small damping, or a critical level. Large means overdamp, damping ratio exists 1. Underdamp means damping ratio below 1. One last thing is that I can tell you that for our civil engineering structures, almost all the structures belong to underdamped scenario for structures. For tall building structures, normally they belong to underdamped scenario. So you start to see many oscillations. For a building under earthquake or under window, the structure will oscillate back and forth, rather than just damp down. If you play with some mechanical problem machine, then maybe they have overdamp. Okay. So we'll spend more time for underdamped scenario rather than overdamp. Overdamp just for your information. This is the derivations that I mentioned before. If you like, you may derive the formula yourself. But I put it at reference because I'm not going to assess you derive this kind of complex formula. You can use the outcome immediately. The outcome that I show you in the next few slides. How to solve this kind of differential equations? You can use the previous approach. Find out the general solution, and then substitute them back to the formula. Find out what coefficients can fit your problem. You can use this approach, something like substitutions. But for this formula, you can see that the general solution is quite complicated. It's involved one arbitrary complex functions, g, time exponential function st. You substitute u into our formula. You have to do some differentiations. D is twice once to give you acceleration and velocity and displacement here. Substitute them into the equation of motion and then do a grouping. This left-hand side are big things equal to 0. You have to find out under what condition this equation is true. What is the meaning of this equation is true? This equation is true means left-hand side equal to right-hand side. Left-hand side equal to 0. Okay? How to make this becomes always true conditions? You have 3 options. The first periphrases equal to 0. Second, g equal to 0, or est equal to 0. You have 3 scenarios, right? The first part equal to 0, or second part equal to 0, or the fourth part equal to 0. Either one of them can make this equation equal to 0. But obviously, we are not going to consider the second one and the third one, because we want to get a more general solution. G equal to 0 means what? G equal to 0 means U equal to 0. No movement. No movement is not our interest, right? Otherwise, nothing to do, right? If G equal to 0, then U equal to 0, which means we are talking about at rest. At rest is not our interest. Similarly, EST equal to 0, again, give you 0 displacement, not our interest. we want to talk about something that will move. That's why only the first scenario have to consider. The first term equal to 0. Yeah, for mathematics, right? That's why we turn that to a reference. Well, solving this equation, find out the required value of s to fit these equal to 0 conditions. And you will find that mathematically, there are 3 scenarios. Case 1, damping ratio equal to 0. Case 2, damping ratio less than 1. Case 3, damping ratio greater than 1. So here I show you mathematically, there are 3 vibration modes: overdamp, underdamp, and critically damped. You can understand this mathematically by solving this equation, although it's not easy. That's why I think it's more easy to understand using graphically, using this kind of picture. Normally, I like this kind of pictures more. You have underdamp, which means you have oscillations. Overdamp means there's no oscillation. The displacement decreases gradually, converge to a rest. And critical means a very ideal scenario, the boundary. But again, you can prove this mathematically, 3 cases. For each case, you can find out the corresponding displacement solution. I show the outcome directly. Critical, underdamp, and over critical damp conditions. Normally, we use the middle one, underdamp conditions. We use the underdamp conditions equations for our structural problems. We use this equation here. Okay, maybe we take another short break at this moment. We have a 5-minute short break. After the break, we will continue to discuss free vibrations. I think we can complete this chapter today. Testing. Okay, let's continue our discussions. Before the second break, we start a new chapter, right? To introduce free vibrations. Free vibrations mean we have a system under low force. The structure oscillates back and forth about the equilibrium positions. Any questions regarding to the previous materials? It involves some mathematics about, say, for example, how to solve differential equations, how to understand the meaning of the displacement function, etc. Now, this is dynamics. Dynamics involve physics, mathematics, and also some of your structural sense. So it's not an easy concept. It takes some time to digest. We can continue our discussions. I would like to finish the whole chapter today. Before the break, we mentioned two scenarios: a system under undamped free vibrations, and then a system with damping under free vibrations. I just discussed a little bit about the phenomenon for a system with damping. I showed you graphically about the vibration mode, damped, overdamped, underdamped. You can understand the behavior graphically, or you can derive the equation mathematically. It involves many symbols. And then before the break, I let you know that for our module, we normally use undamped conditions. Damping ratio less than 1, because for most of the structures. For most of the structures, the damping ratio are less than 1. We stop here before the break. Let us continue from here. If you like, you may also consider the other equations, if you like, for mechanical problems or for the other situations. But for buildings, we normally use undamped situations. U equal to psi, cosine, plus times exponential functions. These things. Psi cosine, just like the response of undamped system that you learned before in session 1. Psi cosine, you can combine this part to a single cosine function. It's just like oscillation. Psi cosine is something related to oscillations. Then what about the exponential functions? We will discuss the physical meaning in the next part. So here is the conclusion at this moment. If you want to solve a free vibration problem for a damped single degree of freedom system, the corresponding governing equation is this one: m double dot plus u dot plus ku equal to 0. For undamped scenario, the general solution will be expressed in this way. It's composed of two parts. One is so-called the decay part, the exponential function. The other one is psi cosine part, oscillation functions. Psi cosine gives you something about oscillation, how it's oscillate with respect to time. The decay part, if you plot exponential function graphically, then you will probably see something like this. Decay curve. The magnitude decreases as time goes on. That's why we call that decay. When you put them together, when you multiply these two functions together, then it will give us a more general free vibration pattern. But before showing you the graph, let me define some parameter. When you take a look on the oscillation function, you can see that the vibration frequency is now equal to omega d. You can compare this equation with the one that we derived in the previous section, session 1. In the previous sections, we use omega n, which is equal to square root k over m. Omega n is called natural frequency, depends on mass. This equation for a damped system the vibration frequency is slightly different from undamped system. The relationship is here. The damped natural frequency, omega d, natural frequency of a damped system. The natural frequency for a damped system is slightly smaller than the original undamped system. It is equal to omega n, the original values, multiplied by square root 1 minus omega, not omega, 1 minus damping ratio squared. This one. Because we are considering small damping ratio is small. When you consider small damping ratio, how small? Let you know some number. Say, for example, for RC structures. For RC structures, the damping ratio, normally 5%. Normally, we take it equal to 5% for RC structures. 5% means 0.05. 0.05 squared becomes an even smaller number, right? 1 minus a small number gives you approximately equal to 1. Approximately, not exactly. That's why you may make approximation here. Then the frequency is approximately equal to the original natural frequency, which is equal to square root k over m. This is one common assumption we make in our calculations. Damped frequency equal to, not equal, approximately equal to undamped frequency, equal to square root k over m. This is one common assumption we make in our calculations. Period. Period, you have similar relationship. Damped period equal to the natural period over square root 1 minus damping ratio squared. But for small damping, you can set them equal to each other for easy calculations. For small damping ratio, you can simplify the equation a little bit. And what about the graph? The graph will look in this way. You can change them to an alternative form. As we mentioned in the previous sections, you can combine sine cosine into one single trigonometry function, cosine. For example, you can combine cosine sine into one single cosine function to make it more easy to understand graphically. Rho means amplitude times an oscillation function, cosine, with a phase angle, theta. And then for a damped system, there is a damping decay function, exponential function, minus damping ratio times natural frequency times the time. You can calculate rho, amplitude, the phase angle, theta, using the equation as shown on the right-hand side of this page. You can convert this to an alternative form if you like. They're equivalent. They're equivalent to each other. So when you answer the problem, you can use either one of them. The first one is the original form, involve sine and cosine separately. This one I think is more easy to use. The second one is more easy to understand. You can see the amplitude, you can see the cosine function, oscillation, you can see the decay directly. When you plot this function graphically on a graph paper, then it is what is behaved. You can see that the vibration amplitude decreases as time goes on. The vibration amplitude decreases as time goes on because we have damping. If you have damping, that means you have energy loss. That's why the total energy, right, the energy here, decreases. Vibration amplitude is associated to the energy, right, the potential energy. That means you have some energy loss in the system. This rate of decay depends on the exponential function, E minus omega damping ratio T, depends on these factors. The larger the damping ratio, the bigger the decay curve, the energy loss. You can compare this one with the original one, I mean the undamped system. For undamped system, if you go back to the section 1, the previous section, there is no energy loss, right? The vibration amplitude remains unchanged. But for damped system, a more realistic problem, you can see that the vibration amplitude decreases as time goes on. There are many formulas, right, in this chapter. Equation of motion for different system, free vibrations. And also we have forced vibration. You will learn in the next topic. Right? This free vibration means you have low force. Forced vibration means you consider external loading. You have different external loading, sine loading, cosine loading, pulse loading, arbitrary loading, periodic loading. You have many loadings. You will learn in topic 6, the next chapter. So you will see many displacement functions in this module. But don't worry, because normally in the quiz examination, I allow you to bring one note sheet. You can put down the formula on your own note sheet. So you don't need to memorize all the things. Okay? Normally in the quiz examination, I allow you to bring your own note sheet. You can put down any example, any notes, any equation, anything on your notes paper. So don't need to memorize all the equation, but you need to know how to use it, when you can use it. Okay? Say for example, this one, this equation is free vibration, damped system. Don't use in wrong scenario. Okay? Sometimes they look quite similar, but don't misuse your formula. Now this is the damped free vibrations. This page shows you the approximation that I made before. Right? Damped frequency, natural frequency. I assume that they are the same value for a small damping scenario. This page just shows you a simple investigation to see how small is small. Say for example, the first column is our the natural frequency for undamped system, omega n. The second column is our damping ratio. I try different values of damping ratio to see the impact. And then the last column is the damped frequency, omega d. You can see that for small damping ratio, say for example, damping ratio 1%, 2%, 5%. When you calculate the damped frequency, you can see that they're quite similar. Undamped and damped are quite similar, approximately equal to 1 in this scenario. When damping ratio reach 10%, 0.1, the value start to change a little bit. Right? The original value is 1, the damped frequency is 0.99, but it's still quite similar, right? Quite similar. So it seems that our approximation, damped frequency equal to undamped frequency, is applicable for most of the building examples. For RC structures, we normally take 5% for RC structures. For steel structures, it can be smaller for steel structures. Say, for example, 2% for steel structures, for example. So 5%, it seems that for RC structures, it seems that our approximation is valid. But in case if you have a system with high damping, in some scenario, in case if your system has high damping, like 50%, then you need to be aware of the assumption here, because it starts to look quite different if you have large damping. But in most of the case for RC structures, steel structures, it seems that this assumption is still valid. Okay, this table just shows you some comparison. If you're good in math, if you're good in mathematics, you can instead of using this calculation, you can use math to prove their relationship. This is the relationship between damped frequency and undamped frequency. You can convert this equation to another form and then plot it on a graph. Then you can see much more clear about the relationship between the frequency ratio, the ratio between damped frequency and omega n to damping ratio. You can see the effect of damping ratio to omega d over omega n. For small damping ratio, like here, for small damping ratio, you can see that the ratio between omega d to omega n approximately equal to 1, which means they are equivalent, that they're the same to each other. For large damping, when damping ratio increase, their ratio become lesser than 1. That means they start to look different. So you can prove this numerically using some substitutions, or you can prove it graphically. Depends on what skills you would like to use. I think using number is more easy to understand. Here, you can prove it using number, using substitutions. It's more easy to understand. Effects of damping. This picture shows you a system with different damping ratio, 2%, 5%, 10, and 20% for a free vibration system. This graph is normalized by the vibration amplitude U over U0, which means it's normalized by the displacement amplitude, so that the maximum value, minimum value is equal to 1 and minus 1. Just make the graph more easy to understand. Normalized by the vibration amplitude. This is one drawing skill. Normalize the displacement by the amplitude. The x-axis we use time normalized by the vibration period. So actually it means 5 cycle, 10 cycle, 15 cycle, and so on. It also makes your graph more representative. Instead of using time, here we normalize time by the period. So it's count the number of vibration cycle, make it more easy to compare among different systems. What we can observe for a system with small damping, say for example, 2%, you start to see many oscillations. If we increase the damping ratio slightly from 2 to 5%, you can see that the vibration amplitude drops rapidly. It's close to 0 rapidly. Let's say, for example, in the original problem, 2% damping ratio. For cycle 15, you still see some oscillation right here. But when you increase damping ratio to 5%, at cycle 15, you cannot see vibration, right? Almost at rest. If you increase damping ratio even further, up to 10%, the system stops at around 10 cycles, right? Or even earlier. You can conclude that the higher the damping ratio, the higher the rate of decay. It stops more rapidly if you have a system with large damping. It makes sense because damping ratio means damping, right? Higher damping means you have more energy loss. More energy loss, the system will stop rapidly at rest earlier. If you consider a system with 20% damping ratio, it just have a few cycles, 1, 2, 3, and then finished at rest, nothing. So this page just shows you the effect of damping. The higher the damping, the higher the rate of decay. So at this moment, you know the response. You know the response of a system under free vibrations. Free vibrations mean a system without any force. No force. The system can be oscillate because you give them some initial conditions, initial displacement or initial velocity. Depends on what system you consider, with damping or without damping. Normally, we consider a system with damping because almost all systems have damping. Undamped is a very ideal scenario. For a system with damping, we have 3 scenarios: overdamped, critically damped, and undamped. We normally consider undamped scenario. Damping measure less than 1. And then you know the solution. I just show you the solution. You can use it directly. So for example, if I ask you the free vibration response of a damped system, then you can use the equation directly. Just fill in the blank, find out the coefficients. What is omega? What is U0? What is U dot 0? What is this one? Just use the given information. Find out the coefficient before the sine and cosine functions. Then you can describe what happened for the system, how it's oscillate, what is the displacement at different time instant. You can use them directly. Don't need to prove it. But use the correct equations, because in the future there are more and more displacement equations under different loadings. The more here, I would like to introduce one useful applications, one useful phenomenon that we observed from free vibration problems. This graph shows you a free vibration response for a system with damping. At the beginning, we have a large amplitude, and then the vibration amplitude decreases as time goes on, T1, T2, T3, T4. The time difference between 2 vibration amplitude is Td, the period, right? Period. At time equal to T1, the general formula for a free vibration system is something like this. rho cosine omega dt plus theta. And then there's exponential function. This is the general formula for a free vibration system with damping. But when we talk about vibration amplitude, at this peak point, at this top positions, cosine equal to 1. Right? When you want to find out the maximum value, then you can set cosine equal to 1. Because cosine is bounded by 1 and minus 1. Here is the positive sign, so I use 1. So at this peak point, the value at at time equal to t1 is equal to rho times exponential function. This one times this one. The middle part disappears. Not disappear, equal to 1. At time equal to t1, you can find out the displacement amplitude at time equal to t1 easily by using substitutions. Similarly, you can find out the displacement at time equal to t2, t3, t4. You can easily find out the vibration amplitude at different time instant. T2, you put t equal to t2 into our expressions. But what is the relationship between t1 and t2? T2 is equal to t1 plus period td. So at time equal to t2, you can also express the displacement function in terms of t1 plus the vibration period, and so on. T3, T4, you can express their value in terms of t1 plus n td. Okay, depends on how many periods you would like to consider after the first one. Instead of considering individual displacement amplitude, here we would like to take the ratio U1 over U2, or U1 over U3, or U1 over U4. Here, to make things simple, I just consider the ratio between U1 and U2. U1, as shown from the picture, it is equal to rho E minus damping ratio omega n T1. U2, I use the expression in terms of T1 and TD. Instead of using T2, I use T1 plus TD for the time. Taking the ratio, it becomes exponential function time with exponent damping ratio omega n and TD. It seems that when you're taking the ratio between two vibration amplitude here, you can find out their ratio easily using the damping ratio, frequency, and their period. You can change this equation a little bit. Instead of comparing U1, U2, you can compare U1, U3, U1, U4, or U2, U3, two arbitrary vibration amplitude. They are related to this factor. But sometimes they may have more than one period, depends on how long you consider. Logarithmic decrement. We take log, we take natural log on both sides of this equation. We take natural log, both sides of this equation. We give them one symbol, although it's not very important, delta. Delta means this lateral log, two vibration amplitude. Natural log U1 over U2. Natural log and exponential function cancel out each other. So the right-hand side, only damping ratio omega n t remains on the right-hand side. Because natural log and exponential function, they cancel each other on the right-hand side. Just the right-hand side just have this exponent remains. Damping ratio, natural frequency, time, damped period. And then they have some relationship based on our previous discussions. Say, for example, period, damped period, equal to 2 pi over damped frequency. Damped frequency can be correlated to our natural frequency, omega n, using square root 1 minus damping ratio square. We just discussed before. So you can cancel some common terms. Say, for example, you cancel omega n here. The numerator, you have 2 pi times damping ratio. The denominator, 1 minus damping ratio square, and then take the square root. We make assumptions. Square root 1 minus damping ratio square, approximately equal to 1. For small damping assumptions, for small damping ratio, a 3%, say for example 5%. 5% taking square becomes even smaller. 1 minus a small value equal to 1. That's why we can make this assumption, because we always consider small damping for structural problems. So denominator become 1. Only 2 pi times damping ratio remains. You can change this equation, rearrange this equation a little bit. Damping ratio equal to 1 over 2 pi times natural log U1 over U2. You can use the displacement response to calculate damping ratio. You can use displacement to calculate damping ratio. Actually, this explains one missing thing that I did not mention before. For a single degree of freedom system, it's characterized by 3 parameters: M, C, K, right? M depends on dimension, depends on the density. K depends on the stiffness of member, right? The size of the beam, columns, the elastic property, etc. I did not mention C actually, right? I just mentioned that it's something related to energy loss, but I did not tell you how to calculate C. This page, fill this gap, tells you how to calculate damping. You can calculate damping using the displacement response. You can do experiment by doing the lab. You can record the displacement history of a system, few vibrations, and then based on your displacement record, using 2 arbitrary vibration amplitude, you can calculate damping ratio, just like here. Damping ratio. What are the definitions? C over C critical, right? What is C critical? C critical, if you still remember, C critical equal to 2m omega n. So using this equation, you can evaluate damping coefficient C using damping ratio. You can evaluate damping coefficient C using damping ratio. Okay? Everything linked up to each other right now. You can evaluate MCK or the parameters. If you know the displacement response, then you can calculate this damping ratio using U1, U2, or U1, U3, or U1, U4. Okay, this one you may call it applications, how to use free vibration response to find out the dynamic properties, MCK, of a system. There's one graph on the top right-hand corner of this page. What are they? It just talk about the assumption that I made. For these durations, we assume that we have small damping. Small damping. Then we have a relationship, 2 pi damping ratio. You can see that for small damping, it's represented by this dashed line. The solid line represents the actual formula, 2 pi damping ratio over square root 1 minus damping ratio square. You can see that they start to derive with each other for large damping. They approximate the same when damping ratio is around less than 0.3, approximately. So below this range, below 0.3, it seems that our assumption here is still valid. The equation is valid for this range. For this range, you can see that the two expressions are similar. But beyond this range, assumes that this assumption is not very correct. Okay? You can observe this graphically. But anyway, for this module, we normally consider a few percent damping ratio. That means within this range. So you can use this equation, like a Riemann decrement all the times in this module, as long as you are playing with free variations. Okay? We are talking about free variations. Remember, okay, the background. We are talking about free variations. This about free variations. Don't use the wrong equations. We can extend our discussion beyond a little bit. In the previous derivations, we considered two adjacent amplitudes, U1, U2, right? But in general, you can consider any two variation amplitudes not next to each other. Say, for example, if you consider the ith term and I plus j terms. Say, for example, the first term and the third terms, or the first term to the fourth terms, they are not necessary next to each other. You can consider any variation amplitudes. Simply call it I and I plus j terms. They are different by j. Okay. So the equation can be modified a little bit. The log decrement, natural log over natural log ui over ui plus 1, two variation amplitude. The I terms and the I plus j terms here equal to j, 2 pi times damping ratio. You just put j right here. Okay, they're different by j terms. Different by j terms. How to get these expressions? You may redo this you may redo these derivations. Instead of consider 1, 2, you may consider 1, 3 or 1, 4. Then you will see one extra terms right here, j. Quite easy. So damping ratio can be calculated using this formula, 1 over 2 pi j, and then natural log ui over the amplitude, I plus j terms. This one is a more general formula to estimate damping ratio using free variation response. You can use displacement to find out the damping ratio, displacement plot. When you read the textbook, they also show you that instead of using displacement, you can use acceleration history, the acceleration, to estimate damping ratio. The textbook showed you that you can also use acceleration instead of displacement. The reasons why the textbook mentioned acceleration because of one very practical reasons. Because they found that for a building, it's more easy to measure acceleration rather than displacement. That's why they give us also one equation for accelerations. But you can see that the expression almost the same. The expression are almost the same, except that you replace displacement using acceleration. You can use acceleration, not only displacement. One simple example, try to use the log decrement equations. Suppose we have a single degree of freedom system. Damping ratio, 1%. Is what enough? Estimate the number of cycles required to reduce displacement by 50%. If displacement is 1, then you are asked to find out the number of cycles required to displacement reduced 2.5. Number of cycles. Free variation problems. If we are talking about the other variation, like under external force, under sine force or cosine force, then you cannot use these equations because we derive based on free variation response. So what you do? You may use classical method, express u in terms of the sine, cosine function, and then by solving the equation, solving the problems, you can find out the time required. But I think the shortcut here is you can use the log decrement that we just mentioned before, these equations. The question asks you to find out the time, the number of cycles required to reduce the vibration amplitude to 50%. Say, for example, if the initial value is 1, then the target is to find out displacement reach 1/2 of the initial values. Say, for example, 0.5. Damping ratio, you know the numbers, right? So actually, you just ask to find out how many cycles J can make the displacement drop to 1/2 of the initial number. So I think for this problem, it's more easy to use the log decrement equation to solve it. These equations. If you use the original formula, U equal to rho cosine, blah, blah. If you use this formula to solve it, then it takes you more time to do so because you need to operate the cosine function, exponential function, one at a time required to drop displacement by half. It's more difficult to solve it if you use the original form. If you use this log decrement equation, then it shows you the outcome immediately. If you take the initial displacement is 1, then the denominator becomes 1/2. You want to know how many cycles can reduce your displacement to 50% of the original number. Initial is 1, then the target is 0.5. Damping ratio 1% given in the problems. 1% damping ratio, which means 0.01. You're asked to find out J. J means the cycle, right? How many cycles between Ui and Ui plus J. By slightly rearrange the formula, move J to the left, and then move the other item to the right of the equation. Then you can find that, oh, J is approximately 11. After 11 cycle free vibrations, the displacement reduced approximately to 1/2 of the initial values. So sometimes if you use this kind of formula, log decrement formula, then you can follow the outcome easily. One application of the log decrement equations. This equation tells you the ratio, something related to the ratio of displacement or accelerations. Example 3. Example 3 is, I think we have seen this structure several times today, starting from topic 4. A one-story building. A one-story building with a mass. This time I tell you the mass, 200 tons. The beam is fractionally rigid beam. This system have damping. The column stiffness, EIC, I give you EIC, 20 mn meters square. Be careful about the unit. Damping ratio, 5%. Damping ratio, 5%. What we're going to do, find our natural frequency. Natural frequency means omega n. Question 2. Try to determine the displacement response, displacement history for this system. Given that the initial displacement is 0, initial velocity, u dot, is 5 meters per second squared. A very straightforward problems, right? Natural frequency depends on stiffness, depends on mass, right? Square root k over m equal to natural frequency. But if you know stiffness, if you know mass, then actually the first one is solved. Second one, displacement history. Displacement history for this single degree of freedom system under free vibrations. If you see these two terms, then you should feel happy because you have the solution. You have the solutions. The one that I showed you before, you can use the, depends on which form you would like to use. They are alternative form, or you can use the standard form with sine and cosine. Something like this, right? These the alternative form for free vibrations with damping. What you have to do, you just need to find out those missing parameter, rho, theta, something like that. You can use this solution directly, but you have to find out those coefficients, rho, theta, the other thing else. So this one just testing you some applications, how to use the equations. For free vibration problem with damping, actually you are asked to solve this one, right? This equation of motions, u double dot plus u dot plus ku equal to 0, free vibrations. But in the notes, I've already solved all the things for you, so you can use the outcome, find it from the notes. Mass, 200 tons, I convert it to kg. If you are aware of unit conversions, if you are afraid to make some mistakes in unit conversion calculation, one way is to convert everything to standard unit. Convert mass to kg, convert force to Newton, convert length to meter. You may do these conversions. Then normally you have no problem for unit conversions if you change everything to standard unit. Although sometimes it will make the number too big or too small, but at least you have no problem about unit conversion in this case. Column stiffness. Column stiffness is 12 EIC of HQ, but you have two columns, column 1, column 2. Two column means you have to multiply the column stiffness by 2 based on metric beam model. So you have column stiffness, you have total system stiffness K equal to 75 times 10 exponent 5 Newton per meter. Natural frequency, square root K over N, K, stiffness, we just evaluated. I use standard unit, Newton per meter. For mass, I also use standard units, kg, 200 times 1000 kg. And then the frequency is equal to 6.12, 6.12 radian per second. Period, if you like, you may also calculate period, although I did not ask you to do so. Period, 1.03 seconds. Damped frequency. For our free vibrations, we have damped frequency, approximately equal to the natural frequency of undamped system. For small damping, 6.12 radian per second. The calculation here is pretty straightforward, but I want to remind you again about the unit. Because sometimes some students would like to use kilonewton for force. Say, for example, if you use kilonewton per meter for stiffness, then you have to change the mass unit to tons. Okay? If you use Kn right here, then mass should be in tons. Simply means multiply both by 1000. Otherwise, your answer will be totally different. What I mean is that if you use Kn per length for the numerator here, if you use Kg for the denominator, then your answer will be wrong because it's different by 1000. Okay, aware of unit conversions. Because I observed this problem many times before, that's why I want to put a remarks here. Displacement. Part 2 asks you to find out displacement history. You can use our response directly. Here I use the standard form. This invoke exponential function, u0 cosine omega dt plus quite a long terms, u dot plus damping ratio omega n u0 over omega n omega d sine omega dt. You can find out this expression from our previous section, section 2. You just fill in the blank. We have initial displacement 0. We have initial velocity 5 meters per second. We have damping ratio 5%. From the previous calculations, we know that omega n equal to 6.12 radian per second. Omega d equal to omega n equal to 6.12 radian per second. So you can substitute all the numbers back to these expressions. Then you have this equation. At the bottom, I plot the graph, let you know what happened for these structures. This is how it's oscillate. At the beginning, 0 here, because we have no initial displacement. So it starts from 0, and then it starts to under positive movement, and then decrease, drop to minimum, and then maximum, it vibrates periodically, following something like aside functions. A very classical example of free vibrations. You can use this formula directly. Make sure that you know how to find all the values. One example to let you know how to use the equations, just fill in the blank, quite straightforward. So if you understand all the things right here, I think the question difficulties is even more easier than simplest method. There's not much matrix at this moment. Just invoke 1 or 2 formulas. One remarks. Up to now, we focus on 2D problems. But in reality, for 3D structures, you may have 2 different stimulus. When the structures vibrate along these north-south directions or east-west directions, they may have different number of columns, they may have different structural system. Just like here, when the structure oscillates about the east-west directions, you have a brace. When the system oscillates about the north-south direction, there is no brace, empty here. It just resists using column. So for 2D structures, you have to pay a great attention to the direction. Which direction you're considering? You may have different structural system. Different structural system give you different stimulus. For 2D, it's easy, but for 3D, be careful about the directions. Which one you are considering? Just let you know in reality what happened. For this module, normally we play with 2D for this module for hand calculation, so we make things simple. But for real case, 3D, be careful about which directions you are considering. If you have different stimulus means you have different period, different frequency. Finally, the last part. The last part is quite short. Application of free vibration. Actually, we have already discussed. Free vibrations. You can use free vibration response, just like displacement, to evaluate damping ratio using the log decrement property, the one that we mentioned at the end of section 2. You can use log decrement property to find out the damping ratio. Because damping ratio is, you cannot calculate damping ratio directly using the structural property. Different from stiffness. Stiffness, you have some chance to calculate stiffness using EI, age, these kind of things. But for damping involves many mechanisms, right? Heat loss, friction, yielding, etc. There is no easy way to calculate damping directly. So here, alternatively, we can calculate damping using free vibration test. Using the displacement response, then you can calculate damping. The last part here gives you some useful information. Damping ratio. Damping ratio. Normally for structures, the damping ratio is somewhere range in between 1% to 5% in general. Steel structures, the damping ratio is normally smaller, 1 to 2%. For RC structures, we typically take 5%. 5% for RC structures. This one shows you a little bit about the range of damping ratio. 3% normally for structures, undamaged structures. That's why we normally consider undamped condition with small damping. Okay, that's why I keep using the small damping assumption throughout our discussion before. Small damping. The second point shows you some rule of thumb. That means some empirical relationships. In the notes, I showed you how to calculate period or natural frequency, right? You can calculate period or frequency using stiffness and mass of a building. But if you want to calculate the period of a tall building, maybe say for example 30-story tall, then how to calculate the period or vibration frequency of this system? For a tall building, it's quite difficult for you to find out a single stiffness and single mass, right? If you do not have K, if you do not have M, then you have no chance to calculate omega and T based on our previous discussions. Firstly, tall building is not a single story structure, right? It's not a single degree of freedom. Tall building is a multiple degree of freedom system. That's why you cannot calculate omega directly in this case. But in case if you really want to know it, then what you can do, you can use some empirical relationship. In our Hong Kong code, Hong Kong mean code, this mean code. For Hong Kong mean code, they give us one simple formula to estimate the radiation frequency, M. They use this empirical relationship, 46 over the height of the building, give you the radiation frequency. Or another more easy formula from the other textbook, the period is approximately equal to 0.1 times the number of stories. You can use this kind of approximation formula to roughly understand the radiation frequency or radiation period. But they are not exact. They just give you some idea about the range of the number, not exact. About the exact frequency, I will let you know later how to play with the calculations at the time when we go back to matrix, multiple degree of freedom system. Summary. In this chapter, topic 5, we introduce the basic idea of free radiation. Free radiations mean we have low force, force equal to 0. We consider two systems, without damping and with damping. Normally, we use damped system. That's why I turn undamped system to gray color, just for illustrations. Normally, we play with damping, system with damping. For a system with damping, the free radiation response can be expressed using this equation. Exponential function times sine, cosine, something like that. You can use it directly. But you have to find out those coefficients, U0, U dot 0, these kind of things. And finally, we discuss one applications. You can use the radiation response to find out our damping ratio using the log decrement equations. Okay, these are all the things we cover in topic 5. So we finished topic 4 and topic 5 today. The thing changed suddenly, right? From matrix to differential equation. Yeah, it takes time to digest the concept because they're totally new things. I believe that different from Sylvus method. For dynamics, the world changed suddenly, become just like mathematics or physics problems. It takes some time to digest the new things. Yeah. So this is the end of this class. Thank you everyone to join this class online or in person. Yeah, if you have no questions, then this becomes the end of this lectures. Thank you very much. Please submit your assignment before the due date, next Friday. 係啦，睇你有冇問題啦。如果冇嘅話咧，咁就完結啦。